Okay, we've talked about the basics of entropy. Think of it as just disorder. We can work out the entropy change delta S for a reaction. We did that in the last video. Now we want to talk about this very important law, the second law of thermodynamics, and it states that for any change, the total entropy, any chemical change or physical change, the total entropy of the universe, of everything, must stay, must either get bigger or stay the same. Usually it's going to get bigger. Okay, so whatever happens, the total entropy of the universe increases. Okay, so let's have a little think about the reaction we looked at in the last video, which was magnesium. So magnesium plus oxygen going to form O2, goes to form magnesium oxide, ionic solid. Okay, and delta S for that reaction we worked out was equal to minus 108.3 joules per mole per Kelvin. Right, so here you may think, right, well, you've got a delta S is negative. The disorder decreases in that reaction because we start off with solid magnesium and gaseous oxygen, and we turn them into just a solid, so it's going to be less disordered. Right, now the important thing here is this delta S is the entropy change of the system, so it's just a reaction. But you know what happens when you burn magnesium? It's very exothermic, isn't it? You get you've been doing that since year 7, burning bits of magnesium ribbon, get a nice bright white flame. It's very exothermic. So what does that do? It heats up the universe. Okay, it heats up the surroundings. So what happens to the entropy of the surroundings? They're getting hotter. All the molecules are flying around more, vibrating more, whatever. And so the entropy of the surroundings increases. Right, so yes, the entropy of the system of the magnesium and the oxygen and that decreases, but that can only happen because to compensate for that, we give a load of heat out and that heats up the surroundings, so that can that reaction is possible because when magnesium reacts with oxygen, and we can work out the total entropy changes. We can work out the entropy change of the system. We can actually work out the entropy change of the surroundings as well, and we can see that that is it's enough to compensate for that. In actual fact, the entropy of the surroundings changes by this formula, which you don't need to know, but just so delta S, and I'm going to call it surroundings, is equal to minus delta H over T, the absolute temperature. So you can see if delta H is negative, if it's an exothermic reaction, a minus makes a plus, so the entropy of the surroundings will increase. And likewise, if delta H is positive, okay, if it's an endothermic reaction, it's going to take in heat, so it's going to decrease the entropy of the surroundings. These surroundings are going to get colder. Okay, so anyway, that's that equation there, which you don't actually need to know. So I'll rub that out. Let's have another little think about water. Okay, so if you get some liquid water and you put it in the freezer, you turn it into water solid, into ice, and we can see from that quite obviously delta S for that reaction, the reaction is negative. So is that breaking the second law of thermodynamics? Well, it's not. No, is it? Because this reaction is actually, well, not reaction, but this change is exothermic. So it's endothermic, beg your pardon. No, it's not. It's exothermic. It's exothermic. So it's going to give out heat. And so it's going to heat up the surroundings. So the entropy of the surroundings will increase. And so, and the surroundings in that case is going to be the fridge. Okay, so the fridge, the entropy of the fridge will go up. And you probably know that if you put your hand down the back of a fridge, it's hot because it takes heat out of the inside of the fridge and then disperses it into the room. Okay, let's just have a think about why is this change exothermic? Why would it be exothermic? Well, what are we doing when we are forming solid water from liquid water? We're forming hydrogen bonds. Okay, then when we form covalent bonds, you get a lot of heat out. It's very exothermic. When you form hydrogen bonds, it's slightly exothermic. You get about 20 kilojoules per mole of per mole of hydrogen bonds formed. It's exothermic. So that's why freezing water is exothermic. Yes, the entropy will go down of the water, but the entropy of the surroundings goes up. So the second law of thermodynamics is not broken. Right, let's just have a think. What's driving this second law of thermodynamics? Why is delta S got to be greater than 0? Right, it's all down to probability. If you just have a think, this is a very simple, very simple way of looking at it. Okay, we've got a classroom. Okay, and I've got a gas jar of chlorine down here. There's a gas jar of chlorine. I say I've got a load of chlorine molecules in there, draw them as little green dots. Right, if I take the lid off that, and allow, okay, and just leave it, there's no drafts in this room, well, you know, with diffusion, what's going to happen is all those chlorine molecules are going to be evenly distributed throughout the room. Diffusion is going to make that. You're 100% certain, really, that is definitely going to be the case. You can have an even concentration of chlorine throughout the whole room. But is it impossible, let's think, that all of those chlorine molecules it could be just, a chance thing that they could all just diffuse up, and at one point they could all be up here, couldn't they? You could, in a gas jar size container, up in that corner of the room. Okay, and all of these ones, they're not here at all. They're all just diffused up there. Now, is that impossible? Is it impossible? And obviously it is no. It's not impossible, but it is very unlikely. So the second law of thermodynamics is just saying, really, the most probable thing will always happen. The most probable thing in this case here is for the chlorine to be completely evenly distributed. Okay, so that's what's driving it. So of course, if you're looking at individual molecules, if you're looking at one atom, could you use the second law of thermodynamics to predict what the atom is going to do? No, you can't, because it's only when you've got very large numbers of atoms that it works. Okay, so we will leave that there and move on to talk about another quantity, delta G, in the next video.